So I have the matrix A, 1, 2, 1, 2, 1, 1, and I want to do a singular value decomposition of it. So A is equal to U sigma V transpose, where U and V are orthonormal, and the sigma contains the singular values. So I will begin by taking the product of A transpose and A. So you can as well do A transpose, but if you do that, you get a 3x3 matrix. Well, if you do A transpose A, you get a 2x2 matrix. So it will be a bit easier. But that is a total valid solution too. You can compute A transpose 2. So if I compute A transpose A, I get the matrix 6, 5, 5, 6. And now I can find the eigenvalues of that matrix. So I compute the determinant of A transpose A, not A, of course, of the determinant of A transpose A minus lambda I. So this is a minus here, minus lambda I. Yes, minus. This is a minus. Yes, and so if you do that, you will get as eigenvalues lambda equals to 11 and lambda equals to 1. Yes, so now we can find the singular values, which will be the square root of those eigenvalues. And remember, the biggest eigenvalues come first. So our first eigenvalue will be 11, not 1, because yes, our sigma sub 1 will be the square root of this lambda sub 1, which will be the square root of 11. And the sigma sub 2 will be the square root of lambda sub 2, which will be 1. Because remember, in the sigma matrix, we put first the bigger singular values and then the smaller ones. Yes, and remember that sigma has the same number of dimensions as A. And so we fill in the rest with the zeros. Yes. So now we can find our eigenvectors, which will be, in this case, the vectors filling in the matrix V, and not U, because we computed that we found A transpose A. If you had done A times A transpose, you would now find the eigenvectors U sub 1, U sub 2, U sub 3. But here we have computed A transpose A, so we will find V sub 1 and V sub 2. Also remember that if your A is a M by N matrix, your matrix U will be a M by M matrix, and your matrix V will be a N by N matrix, and your matrix sigma will be a set M by N matrix. Yes, so remember that in this case, I mean, U will be a 3x3 matrix, but V will be a 2x2 matrix, because N is the number of columns, so here 2, and M is the number of rows, so already 3. So V will be a N by N matrix, so a 2x2 matrix, and so it makes sense that the eigenvectors V sub 1, V sub 2 will be in 2 dimensions. Yes. So if we find the eigenvectors of that matrix using those eigenvalues here, we get V sub 1 prime is equal to minus 1, 1, and V sub 2 prime is equal to 1, 1. And now we need to normalize that. So we get that V sub 1 is equal to 1 over square root of 2 times the vector minus 1, 1, and V sub 2 is equal to 1 over square root of 2 times the vector 1, 1. Okay, square root of 2 because this is the norm of this vector. Okay, so it's the square root of 1 squared plus 1 squared. Respectively, here it's the square root of minus 1 squared plus 1 squared. Yes. Yes, so you have our two vectors V sub 1, V sub 2, and so that will already be our matrix V. Yes, now we can find the vectors U sub 1, U sub 2, U sub 3, because remember U will be a 3x3 matrix, not a 2x2 one. Yes, and so yeah, again you can now compute A times A transpose, and again the eigenvalues will be the same, the non-zero eigenvalues, and then you can find the eigenvectors of this A times A transpose, which will give you your U sub 1, U sub 2, U sub 3. But you can use the shortcut if you remember that U sub I, let's call it prime, is equal to 1 over sigma sub I times A times V sub I. Okay, I might make prime because sometimes you need to normalize it again. You will get the vector if you compute that, but then remember that the U the vectors u, the u vectors also need to be normalized like the vector v is, and sometimes they are not normalized after this computation, so you need to normalize them again. Yeah, so I denoted by prime, because then I mean your ui will be your ui prime over the norm of ui prime. Yes. Yes, so we can find u sub 1 prime, which will be 1 over sigma 1 times a times v sub 1, which will be 1 over sigma 1, that's 1 over square root of 11. Okay, remember sigma 1 is square root of 11. Now we have the matrix A, and we have the vectors v sub 1. So we have this vector here, so we take the square root 1 over, we take the 1 over square root of 2 in front just, and if you multiply A with minus 1 1, I mean the vector minus 1 1, you get the vector 1 1 0. Okay, I mean like minus 1 plus 2, which will be 1, minus 2 plus 1, which will be minus 1, and minus 1 plus 1, which will be 0. Okay, so you get that vector. And u sub 2 will be, u sub 2 prime again will be 1 over sigma 2 times a times v sub 2, which again will be 1 over square root of 11, square root of 11, sorry, not square root of 11, 1 over square root of 1, sorry, yes, it's a square root, no, it's not 11, it's square root of 1, sorry, because the second singular value is not square root of 11, but square root of 1, so simply 1. I mean, that's the square root of 1, that's just 1, yes. So yes, you get 1 over square root of 1, so 1 over 1. So 1 times 1 over square root of 2, again, this normalization factor here. Now again, if you multiply the vector 1, 1 with the matrix A, you get, I mean, 1 times 1 plus 2 times 1, so 3. 1 times 2 plus 1 times 1, so 3. 1 times 1 plus 1 times 1, it will be 2. So you get that vector 3, 3, 2, and yeah, 1 over square root of 2 and 1 over square root of 1, so simply 1, yes. Now we need to normalize it, normalize both vectors. So at the first one, we have the vector 1, 1, 0. We have the 1 over square root of 2 in front, but we don't need this 1 over square root of 11. Okay, so yeah, our vector u sub 1 will simply be 1 over square root of 2 times the vector 1, 1, 0. Okay, this is normalized. And u sub 2 will be, I mean, if we normalize it, it's the square root of 3 squared plus 3 squared plus 2 squared, so square root of 9 plus 9 plus 4, so the square root of 18 plus 4, so the square root of 22. Yes, so this is your u sub 2. And now we need a third vector u, the u sub 3, because remember I said that u is a m by m matrix, so here in this case m is 3 because A has 3 rows, so we need a 3 by 3 matrix for u, so we need as a third vector u. And so again, you simply need, I mean, we can't use this formula here anymore because we don't have a third singular value, I mean non-zero singular value. I mean, if you had an extra singular value but it is 0, you cannot divide by 0, so you can anyway not use this formula. So again, what you do is you just find some vector that is orthogonal to all other vectors you find until now, and then you normalize it. And here we are in 3 dimensions, so we can simply use the cross product, because remember that the cross product of 2 vectors gives you a vector that is orthogonal to the 2 other vectors. And now we will normalize it. But again, if you're in other dimensions, if you're in 2 dimensions, you can remember that if you have a vector AB, yeah, the vector that is orthogonal to it will be, you switch both coordinates and you add a 1 in front of one of both coordinates, so let's make like B, I mean, you could have separated it in front of the A. Yes, and otherwise, I mean, you can, for example, use Gram-Schmidt again, but or some other method that you know, I don't know. It just needs to be a vector that is orthogonal to all other vectors you found until now, all other vectors u, in this case. Yes. Yes, so here we simply take the cross product because you are in 3 dimensions. So we get, if we take the cross product of u sub 1 and u sub 2, we get 1 over square root of 44, so it's 1 over square root of 2 times 1 over square root of 22. And yes, if we take the cross product of the vector 1, 1, 0, and 3, 3, 2, we get 2 minus 2, 0. And now again, we need to normalize that, so we don't need this factor of 1 over square root of 44, because the norm of this vector is square root of 2 squared plus minus 2 squared, so square root of 8. So we simply have that u sub 3 is equal to 1 over square root of 8 times the vector 2 minus 2, 0. Yes. So this is our third vector u, and so yes, now we have our matrix u, which is filled in with the three vectors u, so u sub 1, u sub 2, u sub 3, so those vectors here. And you have our matrix sigma, which will again have the same number of dimensions as A. So it will be a 3 by 2 matrix. You put in the singular values from the biggest to the smallest one in the diagonal. So square root of 11 and 1, I mean square root of 1, so 1. And you fill in the remaining stuff with 0. Okay, 0 here, 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 yes. So this is your singular value decomposition of the matrix A, yes. So again, I mean, yeah, you just apply the formulas. You find A transpose A or A transpose by not forgetting that if you find A transpose A and then find the eigenvalues and then find the eigenvalues of A transpose A, you will get your vectors U V, sorry, not U, your vectors V sub I. And if you find first, I mean, if you find A times A transpose, then you find the eigenvalues. Again, the non-zero eigenvalues will be the same as for A transpose A. But then if you find the eigenvectors, those will be your U sub I. That is, I think, very important to not forget. Yes. Yes. So yeah, and then yeah, you apply the formula. So you use this u sub I is equal to 1, u sub I prime is equal to 1 over sigma I times A times V sub I. And you don't forget to normalize the result because u and v are orthonormal. And also the singular values for the matrix sigma are from the biggest to the smallest one, and and you fill in the remaining space with zeros. Yes, and V is a n by n matrix, where n is the number of columns of A. V is a n by n matrix here, where V is the column is the number of columns of A, and the U is a m by m matrix, where m is the number of rows of A. Yes, and then you have your final result. And remember that if you need an extra vector U or V, but you do not have any more any extra non-zero singular value, you will simply take I mean, you can compute the A transpose, respectively A transpose A, and then do the same stuff again, find the eigenvalues, which should be the same, the non-zero, and then find the eigenvectors. Or you can, I mean, just find a vector that is orthogonal to all the vectors you found, and then normalize that one. Yes. Yes. Yeah. So I think that's it. I hope I forgot nothing. Yes. Yeah. Thanks for watching.